Hello everybody, welcome back from spring break. I hope you guys found some way to enjoy it. I am going to start chapter 11 with our first online lecture, but I'm always available by email if you guys have extra questions, all right? So, I miss you guys. I really wish I could be delivering this in person, but hopefully the videos help. So here we go. All right, chapter 11, 11.1, we're talking about normal distributions. So we've got a couple of concepts that'll help us out with some of these problems. What I'll do for the videos as we go through the last two chapters is I'm going to skip the for you to do problems to make the videos as short as I can, and then I will post the complete worked out solutions to the notes online so that you guys can access those if you want to go back and check your work for those for you to do problems. Okay, so we've got this core concept. And it says this: if we've got a normal curve, which is a normal distribution, where we have a mean we call mu, that is what this character is here. It's the Greek symbol for mu, and a standard deviation of sigma, we've got the following properties. The total area under the curve is 1. About 68% of the area lies within one standard deviation of the mean. So what happens is that middle piece, that's the mean. We see that here. And if we go one standard deviation to the left and one standard deviation to the right, that encompasses about 68% of the total area underneath this curve. And then if we go another standard deviation to the right and to the left, that means we're at 2 standard deviations away. We have about 95% of the whole area under the curve. And then if we keep going 3 standard deviations to the right or to the left, means that we've got about 99.7% of the area under the curve covered within 3 standard deviations. We can interpret the area under the curve as probabilities in a normal distribution. So if we're looking for a specific x value and we want to know what the probability is that that value is between an upper bound and a lower bound, a and b, then we can use the area under the curve in order to find that probability. So that's what we're going to do today. Just a little bit of a background, I guess. I had college professors that really liked to use normal curves when they did their grading. So in college, you might hear this called a bell curve or a forced curve. And sometimes what professors will do is, let's say they gave a test that was way too easy and everybody got like an A. But the professors can't give everybody A's. So what they'll do is they'll recreate a curve where maybe, right, the average was a 92%, so that'd be like an A minus. And everybody above that, that would be the new C. And then 1 standard deviation away would be the new B. And 1 standard deviation would be the new A. Right? That is something that these curves are used for. Now, that's like a really severe case of that, or a severe example of that. But that is what a forced curve will do to you guys in college. So look forward to that one. All right, here's what we're going to do today. We want to find a normal probability. So, sorry guys. First example here. A normal distribution has a mean mu and a standard deviation sigma. An x value is randomly selected from this distribution. We want to find the probability that x is between mu minus 2 sigma and then sigma. So I'm actually going to scroll this page up really quickly. Okay, and this is what we're looking at. We're looking at picking some random x value, and we're looking at the probability that that x value lies between mu minus 2 sigma and then mu. So if we go back up to this example, mu minus 2 sigma is this line right here. And mu, that's our median, that's right there. Or with our mean, sorry, not our median. And so we're looking for the probability that x is between these two values. So we're looking at the probability between mu and 2 sigma and sigma. Now, we were told that we could use the area under the curve as a probability. So the area under that portion of the curve is then 13.5% plus 34%. For following the distribution of the data. So that's going to give us about 47.5% probability that some value of x is between those two data points. All right, give that a try for the 4 U's to do, and then check your work on that as you guys are going through the notes. Okay, we're going to skip those for the sake of time on this, and we're going to take a look at example 2. So we've got a slightly different example here. We've got the following information. The scores for a state's peace officer standards and training tests are normally distributed. They have a mean of 55 and a standard deviation of 12. And the test scores range from 0 to 100. So really quickly, I'm going to draw a normal distribution curve, looks something like that. And I know that the middle bar here is going to be that mean. So I know the mean is 55. That's that middle term. And then we're told that the standard deviation is 12. So as I'm counting out the rest of the test values, if I go 12 to the right, we're now at 67. That's one standard deviation away. If I go 12 more to the right, that puts us at 79. That's 2 standard deviations away. If I go one more, we're at 91 here. That would be 3 standard deviations away. And then we can go backwards as well. So if I take 55 and I subtract the standard deviation, we're looking at 43. Again, we're 1 standard deviation away to the left. Subtract 12 again, which is our standard deviation. That would be the test score 31. That gets us 2 standard deviations away. I'll do one more. If I subtract another 12, that is the 3 standard deviations away with a test score of 19. Okay, what else do we know? Well, from that core concept at the top of the last page, we know the percentages under each curve. So those 2 sections make up 68% of all of the data. So each section is 34. I know this section is 13.5 as well as this. Together, all of that is about 95% of all of our data. This is 2.35, this is 2.35, and then we got that 0.15 going on over here, right, as we get farther and farther away. Okay, we are asked about what percent of the people taking the test have scores between 43 and 67. So based on how I just labeled all of the scores at the top, 43 and 67, we're looking for all of this information, or all the data in between here. So 34 plus 34% gets us a total of 68%. So there's a 68% chance that you've got a score between 43 and 67, right? Or 68% of people score between 43 and 67. It's a pretty hard test, actually, if you think about it. Okay, so then we move on to the next question. The next question is, an agency in the state will only hire applicants with test scores of 67 or greater. About what percent of the people have test scores that make them eligible to be hired by the agency? Well, if we look at the picture that I just drew up here, 67, that was 1 standard deviation away from the mean. And so if we want to look at it in terms of the way that it was written in that first example, example 1, we're looking for the probability that a chosen score is greater than or equal to mu plus sigma, 1 standard deviation away from the mean. Okay? In other words, we are looking for, I'm going to color it in a different color. Let's use orange. The percent of scores above 67. So all of this area down here, that is 13.5 plus 2.35 plus 0.15. That totals to about 16%. Okay. All right. Try C on your own. Take a look at that answer. Post it online with the answer key. And just make sure you guys are good on that. Okay. All right. We're going to move on to the next course concept here. Now, the problem is this. All of the questions in example 2 and example 1 met with the data really nicely. So it matched. All the questions we were asked with example 2 dealt with test scores that were a certain deviation away from the mean, right? So we were only looking at those really important numbers that we got from taking the mean and adding a standard deviation or subtracting a standard deviation. But we all know life isn't perfect. So what happens if we have, or we need to find the probability with data that is not perfect. That means, what if I were asked, or if I was asking you guys about the probability that a score was less than 71, right? 71 is not at a really nice place on this normal curve. And so what we're going to use is in the next course concept. So the next core concept really helps us with not perfect data. So let's take a look. Okay, we've got this. If I can find it. Standard normal distribution table, and a standard normal table. And this is really useful when we're looking at information that doesn't fit on that normal curve really nicely. So what happens is this: we can take that x value, which related to the scores in the last example, and we can turn it into what we call a z value using this formula right here in the middle. We take that x value, which would be that test score, we subtract the mean, and we divide by the standard deviation. We get this z value. And then what we can do is we can take that z value and go to the standard normal table and find the probability that we're looking for. So essentially that's what the table does. I'll let you guys read more about that with all that text. But let's actually apply this in an example and see how it's used. Okay, so example 3, using a z-score and the standard normal table. We've got the following information. Let me see if I can fit all of this in one. Can't. Okay. A study finds that the weights of infants at birth are normally distributed with a mean of 3,270 grams and a standard deviation of 600 grams. And we choose an infant at random. We want to know what the probability is that the infant weighs 4,170 grams or less. So let me make a table and let's see what's going on and see what we can do about it. So if I've got a curve here looking like this, I know if we're looking at the data that is normally distributed, the mean is right in the middle. That is at 3,270 grams. And if I add a standard deviation, which is 600, we would get to 3,870. And then again, if I add another 600, we get to 4,470. Going on again, that would get us to 5,070. Okay, but we have a problem. We are looking for the probability that the infant weighs 4,170 grams or less. 4,170 is not on that curve if I'm following standard deviations here. 4,170, somewhere over here, right, where that orange line is. Doesn't line up perfectly on this normally distributed curve. So that's our problem. We can't use the information that we were using examples 1 and 2 to solve this because our data doesn't line up perfectly. It's not perfect. So what we're going to do is we're going to use that table of values, that standard normal table, by calculating the z value first. So the equation was take x, subtract the mean, divide by the standard deviation. That is going to look like this. Our value of x is 4,170. We are subtracting the mean, which is 3,270, and we are dividing by 600 the standard deviation. That gets us a z value of 1.5. All right, now please go to the table that is on page 2 of the notes, and let's find 1.5 on that table. So go down to the row that says +1, and then go across to 0.5. So row 1, column 0.5, and we get this value, 0.9332. So the probability that the infant weighs 4,170 grams or less is about 93.32%. We would call this the 93rd percentile. Okay. That baby was born in the 93rd percentile. All right, let's try one more like this because these are a little bit trickier. And then we'll do the last example here. What is the probability that the infant weighs 3,990 grams or less? Again, if we're looking at that table with the standard deviations, we wouldn't hit 3,990. And so we're going to use the z-score here. We take the value of x, we subtract the mean, and we divide by the standard deviation. That gets us 1.2 as our decimal. So again, you're going to go to that table, look for the row 1, column 0.2. Find the value. That is 0.8849. So you have an 88.49% chance that infant weighs 3,990 grams or less. We call that the 88th percentile. The child was born into the 88th percentile. Okay, so that's what happens when data is not perfect. We use that standard normal table and then those z-scores. Okay, very last thing, super quick concept. Something that's actually a review of Algebra 1. This was covered in the stats part of Algebra 1, but being able to recognize normal distributions. The way that we're going to do that is we are essentially just going to look at the shape of the curve. So a bell-shaped and symmetric curve means that this has a normal distribution. All right, so the first example here is a curve with a normal distribution. It is symmetric. That means if we divide right down the middle, the left and the right side match up. Okay, we have data that can be skewed sometimes. So if we don't have a nice little curve that's symmetrical, we either have data skewed to the left or to the right. That means that it is not a normal distribution. Okay, so let's take a look at the last 3 examples, and then you guys will be good to go. Determine whether each histogram has a normal distribution. If we're looking at this curve, if I were to sketch a rough curve here, I'd say that's really close to being symmetrical. So because the curve looks symmetric, I'm going to write it. We'll say this has a normal distribution. All right, last example here. That is definitely not symmetric, so it does not have a normal distribution. All right, I have full confidence that you guys can answer that last for you to do. The worked out complete solutions to the lecture note handouts are posted online. Email me if you guys have any questions. I will post another lecture video next week for the topics being covered. Bye, guys.